Hello, in this video I'm going to talk a bit about the regions between curves. So in the region between curves, essentially you're dealing with a top function, which is usually marked as f of x, and then a bottom function, which is marked as g of x. And the goal is to be able to find the area of the region bounded by those curves. Now notice that, we're trying to find the area from A to B, okay? Now, of course, we have this definition that says that suppose that f and g are continuous functions with f is greater than or equal to g of x on the interval a comma b. And we make note that that's a closed interval. The area of the region bounded by the graphs of f and g on AB is, so we have that the area, which we just say is equal to a, is the integral from a to b of f of x minus g of x, and then we have dx. Okay. Now, how we arrive to that is that pretty much, from Cal 1, we might have looked at how we can just form a partition. So essentially what happened is that a partition was made, and you called it P, and you have that the first point is x0, and then from there you just continue making n points, and you just stop at B. Of course, you would have to determine the width of each of those rectangles, so you would have that would be delta x, which is simply just b minus a divided by n. Now, in order to find the area, let's say, of one of these rectangles that's drawn on your closed interval, essentially you would just have to find the area by saying, well, let's choose an interval such as like xk minus 1 comma xk, and then we choose a point. So we have x comma k, x sub k star, and this is going to be in our closed interval from delta xk minus 1 to x sub k. Now, in any case, essentially you have that k is just an integer from 1 and then to n. Okay, so the goal was to be able to find the area of the kth rectangle. So we know that we just need to find the respective heights. So in that sense, that's just saying take f of x k star, subtract g of x k star, and that's going to give us these these rectangles. So from there, we need to take this difference of the two heights respectively, and we need to multiply by delta x. Now, in any case, if I was to add this from, let's say, k equals to 1, well, k equals 1 to n, then that would imply that the area is approximately equal to the series summation of the f of x k star minus g of x k star times delta x from 1 to n. Now, of course, what ends up happening is that if you take, a very large amount of n, so let's say like 1,000, then that area is actually going to get, finer and finer or closer and closer to the exact area, of which we learned that that's essentially just a limit. So if we go ahead and we just apply the limit to our region between the two curves, so like if we have the limit as n tends to infinity of k equals 1 to n of f of x k star minus g of x k star, and this is times delta x, well, essentially we have that this is going to give us the definite integral. So this equals to the definite integral from a to b of f of x minus g of x, and then we just put dx. So essentially, that's how one would get the definition of, the area between the two curves f and g. But make note that, this is only possible if and only if, like, f of x is greater than or equal to g of x on that closed interval from a to b. So what that means is that essentially you just need to apply, top minus bottom, because yes, we do have that the f of x would represent the top function, and then the g of x would represent the bottom function. Okay, well, let's look at an example then. Let's look at the two following graphs. So let's say that we want to find the area between y equals 5 minus x squared, and let's look at y equals to x squared minus 3. Okay, so essentially we just want to find the area. Okay, and this is going to be between. Okay, so one thing of which that we can do first off is look at the graphs of those equations. So if we go ahead and we look at the graphs of those equations, we'll find that it looks something. And yeah, we want to do like a rough sketch, okay? So we have something like this, and then we have that the equations come out like that. Okay. Now definitely this is not to scale, but all that we need to figure out now is where they might intersect, because we can see that essentially the top function is the 5 minus x squared, and the bottom function is the x squared minus 3. But the question becomes, like, where do those two intersect at? So we have that we would set those equal to each other. So 5 minus x squared equals to x squared minus 3. And then from there, let's see. Well, we can add x squared to both sides, and we can add 3 to both sides, of which this is going to give us 2x squared equals to 8, which means that x squared, when you divide by 2, gives you 4. Taking the square root on both sides, you're going to find that x is equal to plus or minus 2. Okay, so that tells us that we can actually find the area of the region bounded by these two curves. Okay, so what we'll do is we'll actually set that up as the definite integral. So we have that we're using the formula of the integral from a to b of f of x minus g of x, and that's going to be the integral from negative 2 to 2 of 5 minus x squared minus, and then you have x squared minus 3, and then you have dx. Okay, so let's go ahead and simplify this a little bit so that we can find the definite integral. So this is the integral from negative 2 to 2, and then we have that this is going to be actually 8 minus 2 x squared, and then from there we can actually rewrite this if we want to. So for instance, first off, I know that this is a symmetrical integral. Mostly you can actually determine that from our region, and then go from where you would have to multiply by 2, so you have 2 times the integral from 0 to 2. Now note that essentially you have that there's a common factor as well, And it doesn't really matter if you factor out the 2 or not, because I have there's a common factor of a 2. So let's go ahead and, we'll go ahead and take out the 2, so this will be 4. So we have the integral from 0 to 2 of, okay, so that's 4 minus x squared, and then that's dx. Okay, so what does this give us? This gives us 4 times, well, remember that the antiderivative of a constant would just be 4x. And then you have minus 1/3 x cubed, and then from there, you have that's evaluated from 0 to 2. Now, take into consideration that when you plug in 0, that is just going to give you 0 because you have all variable x. So with that, we'll have that this is going to be 4 times 2 minus 1/3 times 2 cubed. Of course, this gives us 4 times 8 minus 8/3, of which from there, well, it's up to you if you want to, like multiply that by 3/3, and then that gives you 24 minus 8, which is 16. So here, that's going to give you 4 times 24 minus 8 over 3, and then that's going to be 4 times 16 divided by 3, and then from there you get 64 over 3 squared units. Okay, so this is the answer of the integral that represented the bounded region of 5 minus x squared and x squared minus 3. Now the picture looks something like this, where we have that this is the top region, the 5 minus x squared, and this is the bottom region, the x squared minus 3. Now notice that the symmetry is only with respect to the y-axis. Unless, like, for example, that we had that this was more centered, then in that case, that's when we could probably just say, okay, just multiply that by 4, just by looking at it, because I see that, there's like an imaginary line, and then we have the y-axis, and then now it's divided into fourths. However, note that essentially the 16 over 3 would actually represent that piece if we were to kind of rewrite it with respect to if this was an imaginary axis, that is. But it's all the same. Now let's say that we want to find the area between the following two graphs. So similarly, we want to find the area between, okay, so we'll just say that we have one function which is 3x cubed minus x squared minus 10x, and then we'll just use also the following, y equals to negative x squared plus 2x. Okay, now in this case, it actually is not too bad in terms of like finding that area of the region, but you have to take into consideration that they may not be just one region, that is. So we actually call these compound amounts. The compound amount is essentially, it looks like the following. So here, okay, so I know that this is a cubic polynomial, so really the top function is the cubic polynomial, and then the parabola is the one that opens downward. So in any case, I can kind of see that here we have that f of x is going to be the cubic function. So here, we'll just label that as f of x. And then the parabola is going to be our g of x. But the only thing though is that, again, that it's like you have two regions. So what that means is that to find the area, you have to set up two integrals essentially. So the first integral is going to be the integral from -2 to 0, and then you're going to put 3x cubed minus x squared minus 10x minus, okay, so minus x squared plus 2x. And all of this is just, one giant integral. And then you have plus, okay, so you have to do plus the integral from not negative, 0 actually. So from 0 to 2. Okay, so what that's going to do is that's just going to tell you, well, just take negative x squared plus 2x and subtract, okay, so we'll just do another set of parentheses. Subtract 3x cubed minus x squared minus 10x, and then close it, and then dx. Okay, so it looks like there's a little bit of work to do, but we can figure this out. So the first integral is going to be from -2 to 0, and that's going to be 3x cubed. So here you have that that's going to be a minus 2x, and I can see that the x squares are going to cancel out also. So that's just going to be minus 12x. Okay. And then we have plus the integral from 0 to 2 of, okay, so this is going to be pretty much the reverse, because if you have that this is f times g and this is g times f, then it's pretty much just going to be opposite in sign. So that's going to be 12x minus 3x cubed, and that's going to be dx. So we use the antiderivative rule, so this will be 3/4 x to the 4th, and then we have this will be evaluated from -2 to 0 minus 6x squared, and this is evaluated from -2 to 0 plus, okay, well, this is not too bad because essentially you just have to add 1 power, divide by the same thing, which is going to be 6x squared from 0 to 2. And then similarly, it's just minus 3/4, and then you have x to the 4th, and that's from 0 to 2. Now the main thing is that we need to evaluate these and see what we get. Okay, so we know that if you plug in 0, it's just going to be 0, but we're just going to put 3/4 multiplied by, now -2 to the 4th power, that's going to be 16, but it's actually -16 because you have that, you're taking the difference. Similarly, you have -6, and then you have -4. Why? Because you're taking the difference again. So that's going to be -4. And then you have 6 times 4. Okay, and then minus 3/4 multiplied by 16. Okay, now it looks that the answer is going to simplify nicely. Why? Because you have that this is going to be -12, so you have -12 plus positive 24, and then you have another 24, and then you have minus 12. Okay, now check this out. Okay, so we have that there's essentially that you have the first part if you're going from left to right, or if you just want to say 24 plus 24, you get 48 minus 24 essentially, or 12 plus 12, which is 24. And in either case, yeah, it's exactly that, 24 units squared. So that's going to be the answer to how much our area of the two regions would be. And remember that this is an example of compound regions where you have that you had to partition the integral into one, and then you had to do the other. and then you have to use the appropriate bounds. In this case, it was from -2 to 0, and then from 0 to 2. Note that if you did not have the limits of integration, that you would simply just need to set the equation equal to each other, like 3x cubed minus x squared minus 10x equals to -x squared plus 2x. But, one thing that you can kind of realize is that that actually simplified to essentially 3x cubed minus 12x, which from there you can tell that, the answer was like 3x times x squared minus 4 equals to 0. So you can tell that essentially it gave you 3 points, -2, 0, and 2. So let's go ahead and look at another type of method of integration. So in some cases, you may actually have an integral. So like let's say that you have an integral and that integral looks something like this. And then let's say that you have another like that. So here, let's say that the bounded region, let me do that again. The bounded region is between these two curves. So here we're just going to notate that this is going to be C and this is going to be D. So let's just furthermore state that the function you will have on the right side is f of y, and then the function on the left side is going to be g of y. Now, this pretty much gives you the exact same definition as before, but with respect to the y-axis. Yeah, okay, so we have that. Well, let's do it like this. Yeah, okay, so we just need to make sure that we define our integral such that the cross section is actually perpendicular to the y-axis, but it's still with respect to y. So what that means is that the area of the region, it's approximately the series summation of k equals 1 to n if I take a partition and then I say I have f of y, let me just do that again, f of y sub k star minus g of y star times k, and then you know that that's going to be multiplied by delta x. Okay, but if we take the limit as n tends to infinity, that's going to actually give us that the limit of the series summation from k equals 1 to n of the difference of our two functions from right to left, and I'll write that down in a minute, that this is going to equal to the integral from c to d of f of y minus g of y, and then we have that that's going to be dy. Okay, so the differential actually is dy. Now, in any case, we can actually write this as right minus left. So we have the right function, and then we have the left function that we'll be looking at. So now, what we want to be able to do is to just find the integral of a function by, rewriting the orientation essentially. Now, let's say that we want to find the area, bounded by y equals x to the 2/3 will also include y equals to x minus 4. And I'm just going to put y equals to 0. Really, I should put x equals to 0 as well. But we're going to see like that if they're bounded by all these curves that it should work out. So if I was going to draw the region, so so drawing the area or the shaded region basically, okay, so here we're going to draw our graph of x to the 2/3, and it's going to look something like this. But then we also need to draw x minus 4 equals to y, or y equals to x minus 4. So in any case, let's go ahead and put it right about here. And we can see that these two cross, right? Okay, so the question becomes as to like what is the point of intersection? But we know that one of these is right here at 0 and 4. Y equals to 0, that's where we get bounded by this part right there. So if you want to put that so that you have it, and then shade your region. Okay, now a good question might be, how do we set up this integral with respect to x, okay? So if I was going to rewrite this in terms of x, then in that case, one thing that you would have to realize is that the area is going to be equal to the integral from 0 to, now notice that this point right here is 4, and this point over here is 0. This point over here, actually we don't know it yet. Let me see if I can go ahead and do that. Y equals, yeah, I think it's going to be 8 comma 4. 8 comma 4. Okay, so we'll just go ahead and just write that down, 8 comma 4. Now, okay, so we have that the integral is going to be from 0 to 4, and then you're going to take x to the 2/3, but you're subtracting essentially just 0, okay? So in that case, we don't need to put anything, so dx plus the integral from 4 to 8, of which that's going to tell you to take x to the 2/3 minus, okay, so that's going to be minus x minus 4. And that's dx. And we'll just put another extra set of parentheses. Okay, now this integral is not too bad. And, you know, yeah, so that's when we have that the region is basically in 2's, and you have a vertical rectangle. But what if we go ahead and we use our definition of which allows us to just say, well, I want the cross section to be, you know, a simple rectangle but perpendicular to the y-axis. Okay. Sometimes I do forget to put that, so x and y. Now if that's the case, then of course we just have to set up the integral just a little bit different. How? Well, first off, you will just solve for each one with respect to x. So we can tell that essentially that the x 2/3, that's just going to give you x is equal to y to the 3/2. Okay. The other equation will give you that x equals to y plus 4. Now, how this makes it a lot simpler? Well, I used to kind of imagine if I was like going to rotate my axes that I am looking at it from right to left, but if I do that, if I rotate it, then now I can look at it as top minus bottom. So it's almost the same thing in a way. So we take the area is equal to the integral. Okay, but now we just need to figure out what is our limits of integration, of which it's actually just going to be from 0, not to 4, to 8, of which from there, actually I was correct, sorry, it's supposed to be 4. Okay, so 4, and we have y plus 4 minus y to the 3/2, and then this is going to be dy, and then from there, we just have y squared, and then we have plus 4y minus, okay, but that's going to be negative 2/5, and then you have y to the 5/2 as well. Okay, but you're only evaluating it from 0 to 4. Now, interestingly enough, if you plug in 0, you're just going to get 0. So what that tells you is that the area of this is going to be 4 squared plus 4 times 4 minus 2/5 times 4 to the 5/2. Of course, when you simplify this, you're going to get 32 because you have 16 plus 16. And then the square root of 4 is actually going to be 32, but minus, so 2 times 32 is 64. So you have 64 over 5, of which from there, let's see, we have 32 over 1, so that's going to be 160. Okay, so 160 minus 64. Whoops, I think, yeah, actually, let me change this a little, because I just realized a little small or huge typo. So this is going to be divided by 2, and that's divided by 2. So in actuality, that should change things. That'll change things, yeah, most definitely. Okay, so 16 divided by 2, that's actually 24. 16 divided by 2 is 8 plus the 16 is 24. And then that's going to be over 1. So that's going to be 120 minus 64 divided by 5. And that's going to give you actually 56 over 5. Okay, that makes more sense actually. Okay, so the answer is actually 56 units squared. Okay. Now, what if we wanted to look at an example such as like something as easy as a parabola? So like if you had a parabola y equals to x squared, and then you were looking at also y equals to, let's say, 2 minus x, but you want to restrict it to the first quadrant. Okay, so what that means is that looking at the graph, it'll look something like this. Of course, you have that the region, since it's in the first quadrant and it's bounded by the two graphs, well, let's say that you wanted to find it bounded by the x-axis. So yeah, perhaps like we'll just go ahead and include the x-axis. Okay, because otherwise if it's in the first quadrant, it could actually be any of these four. Yes. So, let's see. That means that we're looking at this region right here. Okay, so that means that what would you do to find the area? Well, in terms of the dx, you have that the area is going to be equal to, okay, so it's going to be equal to the integral from 0 to 1 of x squared dx plus, okay, but now you have the integral from 1 to 2 of 2 minus x, and that's dx, okay, but that's telling you that, you know, you're using basically just two integrals. But the question then becomes, what about using dy? What would that integral look like? Okay, so think about that in terms of like, how you could probably work that problem out in terms of using the differential dy, which in this case means that the cross section is horizontal or perpendicular to the y-axis. So, as a hint, I can tell you that, well, x is going to equal to the square root of y, and you have that x is also going to equal to 2. So it's going to be 2 minus y. So these are your two functions, okay? And then, of course, from there, you could probably figure out that it's definitely going to be bounded by 0, and it's going to be up to 1, essentially, okay? So in that case, like, you can see that the right function is definitely the linear one, and that the nonlinear function is going to be the left function. Okay, so that's going to be kind of interesting, especially as we go ahead and we think of, solids of revolution, whether it's about the x-axis or even the y-axis.